Having prepared the background, we will now look at the modal analysis. Our aim is to solve the physical equations of a coupled multi-degree of freedom system, such as this one. The equations are coupled with each other, so they are not very easy to solve. So in order to solve them, we follow such a procedure. What we do is we transform them to the so-called modal coordinates, which are uncoupled, which give uncoupled equations to us, in which case we get, instead of n degree of freedom coupled system, we get n uncoupled equations, which are n single degree of freedom systems, which can be solved quite easily. So that solution will give us the modal solution, such as this one. And once we obtain the modal solution, then using the transformation backwards, using the inverse transformation, we can obtain the physical solution. So this difficult solution of the physical equations can be rather accomplished easily with the modal analysis. And also the modal analysis is a very successful, very useful tool for the analysis of vibrating systems. So we will go into details of it now. We will first look at the undamped vibrations and free vibrations. That is, we have no forcing on the system. We have a mass spring system in the multi-degree of freedom context. We have initial conditions such as x0 equals x0, x dot of 0 is v0. We assume a harmonic solution, and that leads to a eigenvalue, generalized eigenvalue problem. We obtain the natural frequency squared, the eigenvalues, and the mode shapes, the eigenvectors. And then we normalize the eigenvectors or the mode shapes so that they are mass normalized. This triple product, Ui transpose and Ui, becomes a 1 for each of the eigenvectors. Okay. Then we formulate a solution. We say that our solution is basically sum of linear combination of the modes of the system. Ai is a scalar, phi I is a scalar, this is an amplitude, this is a phase angle, and they are to be determined from the initial conditions. UIs are determined from the eigenvalue problem, they are the mode shapes. So our solution is a linear combination of the modes of the system. So if we try to find the coefficients from the initial conditions, how we do that is as follows. The initial conditions, as we see, are x of 0 equals x0 is here. And that is equal to, from the previous equation from here, if you substitute t equals 0, you get the following expression. And for the initial velocity x dot of 0, you take the derivative of that expression, and then set t equals 0, you get the following expression. Now the crucial thing is we multiply these expressions by uj transpose times m. Well, it's not very obvious, but once we do that, it will become clear. So on one side, you get uj transpose mx0 equals this thing multiplied by uj transpose m, etc. Okay. Now you have a summation here, as you see, of n terms, and we know that the eigenvectors or the mode shapes of a vibrating system are orthogonal. So except for the case when I equals j, this is the case for I equals j, these terms will all be 0 because these terms are all 0 to begin with, as we know from our previous lectures. Okay, when I is equal to j, well, this thing, as we know, is equal to 1 because we have normalized the eigenvector. So is this one, this is equal to 1. The rest of all these triple products are 0. So what we get is Aj cosine phi j is equal to Uj transpose Mx0. Similarly, we do the same thing for the velocity term. Uj transpose mv0 equals this. And we again have a summation of m terms in which all terms except one is 0, and that term is the term in which I is equal to j. Okay, this term. I is equal to j, so instead of I here, we put a j. All the rest are zeros because of the orthogonality of the eigenvectors. Again, we get this term is equal to 1, so we get Aj omega j sine phi j. So we get two equations in terms of Aj's and phi j's. And note that we can divide these terms to each other, and Aj's are going to cancel, and we will have sine over cosine, which is tangent, so we can solve for it. And that's what we will do. If you divide these to each other, you will just get the phase angles, as you see here. The phase angles can be obtained from these equations. By the way, this looks like a matrix, but actually these are just scalars. And Aj terms are, you simply square this term and this term. So cosine square plus sine square becomes a 1. So you can solve for Aj as well, as you see here. Therefore, you can solve for the coefficients. And once you solve for the coefficients, the solution is very simply x of t equals ai times ui cosine omega t plus phi phase angle. Okay, this is the generalization of the free vibrations we did for the second order systems. And we do something kind of similar for forced vibrations. We have now forced vibrations. The vibrations have a forcing term. And on top of that, we might have initial conditions. Okay? We do the same thing. We solve the eigenvalue problem, obtain natural frequencies, mode shapes. We normalize the mode shapes. And now we form the modal matrix, P. P is our modal matrix, in which we just stack the mode shapes of the system, and each of these are mass normalized, by the way. And then we do the modal transformation. Modal transformation is simply x equals pq. Now, as we know here, this is x double dot. Pq double dot is x double dot. This is x is equal to f of t. We multiply this equation by P transpose from the left. So we get something like this, P transpose and PQ double dot plus P transpose KPQ is equal to P transpose F. But we know that these are mass normalized. It is made up of mass normalized eigenvectors. So this triple product is going to give us an identity. And this triple product, P transpose KP, will give us a diagonal matrix in which the diagonal terms are the natural frequency squared. So we get uncoupled modal equations, and the forcing terms are the generalized forces, which are obtained by P transpose F. So we get uncoupled modal equations, n of them, like this, qi double dot plus omega I squared qi is equal to capital Qi. In which case, all the equations are uncoupled, they are unrelated. We have n single degree of freedom systems whose solution is kind of easy. But there is one more thing that has to be done, and that is the initial conditions. The initial conditions, the physical initial conditions, should also be converted to modal initial conditions. And for that, we again use the modal transformation, x equals pq. P is the modal matrix where the mode shapes are normalized. Well, the back transformation is, if this is P, it should be P inverse, okay? Well, you can just take the inverse of P, but there's an easier way. We know that P transpose NP is an identity if P is mass normalized. Okay? In that case, well, what we can do is Q of T is equal to P inverse X of T. We know this. We just multiply it by P transpose NP, which is an identity. It doesn't change anything. We also multiply it from this side. But we know that this thing is an identity matrix. So it cancels. So this thing is an identity matrix. So what we get is Q of T is equal to P transpose MX. And if you take the derivative of that, Q dot transpose is equal to P transpose MX dot of T. We have a dot here. Also, we have a dot here. That's missing. Okay. So inverse of a mass matrix is equal, inverse of the modal matrix is P transpose M, and P is mass normalized. So instead of taking the inverse, you just take the transpose and multiply it with the mass. So the initial conditions for the modal equations are obtained as follows. Q of 0 is P transpose M x0. Q dot of 0 is P transpose M x dot of 0. Here you have again. Okay, if you have harmonic forcing, let's say that we now consider the forcing term, not the initial conditions. If you have, if you use the modal transformation x equals pq, you will be using qi double dot plus omega I squared q is equal to something times sine omega t. This is obtained from the amplitude is obtained from the modal transformation. You know, it is P transpose times F0. Okay, it gives you the following. Assuming an harmonic solution, again, the second derivative of the harmonic solution is given as follows. You substitute that into the following equation, and you can solve for the amplitude of the harmonic motion. So the motion amplitude, our motion is equal to something all times sine omega t. And note that there is a term in the denominator like omega I squared minus omega squared. Note that if the forcing frequency omega is equal to the ith natural frequency, in that case you will have a resonance, in which case the modal amplitude will go to infinity. So will the physical amplitude. Okay, so the still, the concept of resonance is still valid for multi-degree of freedom systems. And the total solution is obtained from back transformation. These are the modal solutions. We have n of these, 1 to n. And you put them together. Q is equal to all these terms put together. X is all these terms put together, all the physical coordinates put together. And you obtain the physical transform solution from the back transformation. X equals PQ, that's our original thing. By the way, we have only considered the steady state response. We didn't consider the initial conditions here. The initial conditions were considered in the previous page, as you remember. There is an example here. This is the example we have done before. We assume that all the masses and the springs are the same. Springs are K, masses are M. The first two forces, F1 and F2, are zeros, but F3, which is not very well shown here, is 100 sine 2 over 3K over MT, let's say. Well, we solved the eigenvalue problem. This is solved already before, okay? We have solved this in a previous example. The mode shapes are mass normalized. We have divided them into 1 over root m in all of them. Since all the masses are the same, you just divide it by 1 over root m to mass normalize the mode shapes. So the modal matrix P is just stacking the eigenvectors, mode shapes, together like this, and multiplying it 1 over root m. So once you follow the procedure we have done, the uncoupled modal equations become from P transpose MP and P transpose KP is equal to P transpose F of T. And you get three uncoupled equations like this one. This is the first equation for the first mode. This is the equation for the second mode, equation for the third mode. And each of them have different forcing terms, as you see. The solution is obtained from omega I squared minus omega squared qi0, etc. qi0 terms are these terms, as you see. These are the qi0 terms. And omega is 2 over 3 root k over m here. So once you obtain the solution to each of these, these are, from here you can obtain the solution. I don't go into details of it, but the modal solution can be obtained as you see from here. It is the three modes have different amplitudes, and as you see, the first mode has the highest amplitude, second mode is the second highest, and the third mode has the lowest, because the forcing frequency, which is 2 over 3 root k over m, is close to the first natural frequency, which is 0.58, whereas this one is 0.66, as you see. Okay, so since they are close to each other, the amplitude is close to the resonance, and the first mode is dominant in the response. Then, after obtaining Q of t, we just obtain the physical solution from x equals PQ, which gives you the following physical solution: 153, 238, and 270. These are the physical amplitudes, and the amplitude contains also a 1 over k term, but that doesn't matter really. So that's all for the for now.